This is Precalculus section 2.2 notes. Before I begin going through the examples in the notes, I want to just write down that if you look at some point on page 166 in your textbook, there's a really nice table that has pictures of all of these function types, which might be useful to you as we start reviewing this material. You need to look at a picture of what a absolute value function looks like or what a quadratic function looks like. That's a great resource, okay? All right, so we're going to begin with a linear function. F of x equals x plus 2. You could think of this as y equals x plus 2. This is a y equals mx plus b function. However, notice that we do have a given domain here. Okay, so we'll talk about what that means. So if we wanted to graph this, one way we could do it is we could make a table and we could say, well, let's plug x values that are in the domain. Well, if the domain is only x values greater than -3, how about if we start with -2 then, and do -1, and do 0, and do 1. If we wanted, we could add another row here and do 2 as well. And then we start plugging these in, okay, and into our function for x. So -2 plus 2, that's going to give us 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. Right, I'm just plugging those numbers in. And then I plot these points. -2, 0, -1, 1, 0, 2, 1, 3, and 2, 4. Okay. And I can draw this line, okay, but the line only goes from here to, and I'm going to have to put an open circle right there because we're not including -3, so we have to show that with an open circle. Okay, so perhaps this is part of a piecewise function, and that's why we have kind of just this chunk of the line that lives between -3 and +2. But this is a linear function. And I want to remind you as well, when you look at this function, that another way that you can graph linear functions when they're in slope-intercept form is you would start with your y-intercept, which is 2. Okay. So I would plot my y-intercept right there at 2, and then my slope is 1 over 1. So I would go up 1, right 1, up 1, right 1, or down 1, left 1, down 1, left 1. And that's another way to plot your points, and then you connect your line. Okay, so you can graph with a table, or you can graph using y equals mx plus b rules. Our next function is a power function. Okay, so this particular function is x cubed minus 1. Now I want to remind you that when you have even powers, they are always going to make parabolas. And when you have odd powers and you graph them, they are always going to make snakes, okay, shape-wise. So since we are graphing f of x equals x cubed minus 1, this is going to be a snake. So I know what the general shape of the graph is going to look like. But this -1 right here, when we did these in Algebra 1, we called this value right here a k value. And if k is -1, that tells us that our graph is being shifted down 1 unit. Okay, so one way we could do this is we could just graph the parent graph of x cubed, which passes right through 0, 0, and has the point 1, 1, and has the point -1, -1, and we could move all of our points down 1. That's one option. Another option, if you're not familiar with what the graph looks like, is you can certainly make a table. And a good basic table, my favorite 5 I call them, is -2, -1, 0, 1, and 2. I call that my fave 5 when I'm graphing. Those are always good x values to choose. So if we plug those in, -2 cubed is -8 minus 1 is -9. -1 cubed is -1 minus 1 is -2. 0 cubed is 0 minus 1 is -1. 1 cubed is 1 minus 1 is 0. And 2 cubed is 8 minus 1 is 7. Okay, now we can go ahead and we can plot these points. 1, 2, 3, 6. Okay, so 2. I'm noticing that when I look at my graph here that counting wise, I can't really go down to -9 and up to 7 very well. So what I'm going to go ahead and do here is I'm going to divide each one along the y-axis in half so I can do a better job of plotting my points here. I'm going to go ahead and do the same thing just so that I don't get confused. I'm going to do the same thing on the x-axis. So I'm keeping the counting the same on my x-axis and my y-axis. So now when I plot my points, -2, -9, so 2 to the left, and then down 2, 4, 6, 8, 9, -2, -9 is going to be right there. And then -1, -2 will be right here. 0, -1 will be right there. So there's my shift down 1 because that's the center of my graph. And then 1, 0 will be right here. And 2, 7 will be right there. So there you can see my standing snake, I call it. The next graph is about root functions. Remember, roots can be cube roots, fourth roots, fifth roots, sixth roots, and they do look different. So even roots kind of make a hook shape and they have a distinct starting point because you can't put negative numbers under even roots. So even roots always look like that, whereas odd roots, you can have negative and positive values, so that's going to live everywhere. So our even rules have a very distinct domain where x has to live. Our odd roots is all reals. X can live anywhere. So again, I'm just going to start by making a table, okay? But I want to remind you of something. When we learn this in Algebra 2, we always call this part of the graph the parent graph. And we know what the square root of x looks like. I graphed a rough graph of it right there below the graph when I said it's even, right? And so then we have this changed form of our graph. So this is like the shifted form, I guess we could call it. Y equals a times the square root of x minus h, that's under the radical, plus k is outside the radical. So remember that this h and this k, these are shifts that move the graph left and right and up and down. So if we have this -3 underneath, that is an h value, okay? So that tells us that our h value is +3 because it's always opposite of what you see. And that means that our graph is going to be shifted 3 to the right. So if you know what the basic graph of a square root function looks like, you can just go ahead and graph the final graph. However, if you don't, okay, that's okay. You can always plug x values in. But keep in mind that the smallest x value that you can plug in here is going to be 3 because anything smaller than 3 would create a negative number under the square root. So if I go ahead and I plug in 3, okay, 3 minus 3 is 0 and the square root of 0 is 0. And then if I plug in 4, 4 minus 3 is 1 and the square root of 1 is 1. Okay, so and if I plug in 5, I'm going to get some yucky numbers. I like working with perfect squares. Okay, so something minus 3 has to make a perfect square. How about, let's see, 7 minus 3, okay, because that'll make 4. And the square root of 4 is 2, right? And then finally, if we wanted to make a 9 under the radical so that we would have a square root of 3, then it would be 12 minus 3, which gives us a square root of 9, and the square root of 9 is 3. Okay, so again, I got those just kind of by thinking backwards about my radicals. If you'd like, I can go ahead and graph with I'll graph these points first. So this is 3, 0, this is 4, 1, 7, 2, and 12, 3 would be out there. Okay, so that's what my final graph's going to look like. Now my parent graph, hopefully you remember this, the parent graph for a square root function is always 0, 0, 1, 1, 4, 2, and 9, 3, right? That right there is the parent graph. So that's the graph that we're shifting around left or right, and if there's an a value, then we might be stretching it or shrinking it as well. Okay. Our next type of graph is called a reciprocal function. You may or may not have had experience with reciprocal functions in the past. This is just our introduction to them. We're going to talk about them in a lot more detail later on in the school year. But this graph has a vertical asymptote at x equals 2. Remember, an asymptote is a line that a graph approaches but never crosses. So it's got a vertical asymptote at x equals 2. That's because x cannot equal 2. Hopefully you can see that if x were 2, that would make our denominator 0. We can't divide by 0. That's bad, right? So we have a vertical asymptote at x equals 2, so our graph can never touch that point. And we have a horizontal asymptote at y equals 0. And that is the nature of a reciprocal function. And again, I promise we will talk more about this as the year goes on. So I'm going to go ahead and I'm going to sketch in my asymptotes. I've got a horizontal asymptote here at y equals 0. And I have a vertical asymptote here at x equals 2. Keeping in mind, these are points that the graph is going to approach but never cross. So now, to figure out what this graph is going to look like, I'm just going to go ahead and make a table of points. So I'm going to choose x values. Obviously, I'm not going to choose x equals 2, but I'm going to choose x values on the left side of my asymptote and on the right side of my asymptote. I'm going to keep it simple, though. So how about if I just do 4 and 3 on the right side of my vertical asymptote, and I'll do 1 and 0 on the left side of my asymptote. So when I plug this in, 1 over 4 minus 2 becomes 1/2. When I plug in 3, 1 over 3 minus 2, that becomes 1 over 1. 1 over 1 minus 2, that becomes negative 1. And when I plug in 0, 1 over negative 2, that is negative 1/2. So now I can go ahead and plot these points. When x is 4, y is 1/2. When x is 3, y is 1. When x is 1, y is negative 1, and when x is 0, y is negative 1/2. This isn't much to look at right now, I understand, but this does give you an idea of the basic shape. A reciprocal function is going to have two branches that are going to approach the asymptote in both directions. So this is the general shape of a reciprocal function. Absolute value functions. This is review from Algebra 2. Remember that an absolute value function in standard form looks like y equals a times the absolute value of x minus h plus k, where the vertex is going to be the point hk. But keep in mind that when you are looking at the equation, the h value that you see, the sign is going to be opposite what you see. Okay, so when we graph this, oh, and one more thing I want to point out too, our a value here, this is always the slope of the right side of the v. Remember, these make v shapes. So that a value always gives you the slope of your right side. So for this particular function, f of x equals the absolute value of x minus 2, our a value is 1. Okay, so that means our graph is going to go up 1, right 1, up 1, right 1 on the right-hand side. And our vertex, our h value here, it's x minus 2 inside the bars, so our h value is positive 2. And since we don't see a plus or minus after the bars, that tells us that our k value is 0. Okay, so I can graph this right now without even making a table, okay? Because I know my vertex is at 2, 0, and I know my slope is up 1, right 1, up 1, right 1, up 1, right 1. So this gives me what my absolute value function looks like on the right-hand side. And then the left-hand side is just going to be the mirror image of that. So up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1. If you want to make a table, you certainly can, and I'll fill in a table for you, okay? But I recommend that you just graph it based on what you know about the equation and what you know about your shifts. Oh, hang on. I apologize, I just erased my table. I realized I was looking at the wrong problem. So let's back up a second here. Okay, if we're going to make a table here, we're obviously going to plug in some x values around our vertex. So I might choose x values of 0 and 1 on the left side of my vertex, because my vertex is at 2, and then I would maybe choose x values of 3 and 4, right? And so then when we plug those in, 0 minus 2, absolute value of negative 2 is 2. When x is 1, 1 minus 2 is negative 1, but the absolute value of negative 1 is 1. When we plug in 3, 3 minus 2 is 1. Absolute value of 1 is 1. And when we plug in 4 minus 2 is 2, absolute value of 2 is 2. There we go. My apologies on that one.